So after understanding the addressing scheme, let's take few more instructions. So have you done anything on the timers and counters in the lab?
Yes, sir.
Okay, okay. So let's continue the discussion on that part so that you will understand them even better, whatever you have done experiment with timer right now. There are events basically which we need to time and which we need to take some decisions actually, because PLC otherwise it's keep on running a continuous program. It will be reading inputs and then it will be executing the output, basically whatever is written in the program. Now, when we look forward for certain timing events actually, or we want to take some action after certain objects being counted, we would like to perform some action, whether to stop the conveyor or start the conveyor, or maybe actuating a cylinder. There may be multiple actions that may be required. So in industry, you will find that there are a lot of need that you will be timing an event. So whenever we say that timing an event means whenever there is an input available, you want to take some action after a certain delay. Either you will be creating a delay immediately after the input is available, or you will be taking or creating a delay once the this input is off actually. So that there are two type of timers basically we need to understand. We call them T on and T off, on delay timer and off delay timer actually. So if you can understand this, we call them, this is your on delay and this is off delay. So what we will do, we'll try to understand the behavior of these timers, and there is another similar timer as T on, and which is a retentive on delay timer, that is an RTO. And then we'll quickly see the count up and count down instruction because they are being used for counting the events. So whenever we go for a ladder logic programming, these timer instructions will be appearing like this. So you can just go to the development environment. You can select the timer instruction and you can add this timer instruction into the ladder logic. We need to understand what are the key information that we need to write, because earlier when we were using an input output instructions, we are only mentioning the address of that input and output. But when we go for timers and counters, we need to put additional information into the timers and counters. So these are the information that need to be filled in this block whenever you will be using it. Another important thing we need to see, timer on and off, they will always be initiated or actuated with some input whenever you want to start the time, when you want to start the time. So that is where this instruction is always coming on the right hand side in the ladder. It means that this is a kind of an output instruction. So before that, you have to add some input here. So if you see that all the timer blocks have one input to be connected here, and which will be enabling or disabling the timer. And there is a certain behavior of the timer based on this input signal available that we need to understand. And rest of the information, we will be configuring the timer with this information. And there are two important bits over here, EN and DN actually. So there's an enable bit and there is a done bit actually. So how the status of these bits will be changing, that also we will be understanding, so that we will be utilizing the status of these bits to take some action. So we'll see that what is the function of the enable and done bit. Same is with the counters also. So counters and timers have a similarity. The difference is coming only the timer has a time base. So if you can see here, there's an option to write the time base over here. While there is no time base in the counter, rest of the most of the parameters are the same. So in that case, we'll see that first is the address here. Then we will be specifying the time base. Then we will be writing in a preset value, and there's an accumulated value that keep on changing as the timer continues. And timers are also being utilized as a counter, because in this case we call them ticks actually. So timer ticks are there. So it's almost like a counting something. So there's something happening in the background. It's like your stopwatch is ticking. So that is how the terminology has been picked up. So it ticks that every time base it will be incrementing by one. That is what the ticks means. That is how whenever we write the time value, we will be writing in the preset values. and preset values are values which is to be understood with the time base. For example, if I'm writing in a time base 1.0, it means that my timer is ticking every 1 second. And then when I write the preset value 400 means I would like to create a delay of 400 seconds. So this time base has to be multiplied with this preset, then only you will be understanding that. If I put a time base as a 0.1, then if you see here that's a 400, then the every time the timer is ticking is 400 into zero point 0.1, that is 40 seconds. Total will be 40 seconds, and every 0.1 second the timer will be ticking. So that is how we need to interpret these values of the time base and the preset in this case. And same is with the count up and count down. Now there is no time base, so only we will be counting the objects here, and the preset value is there to match that count, and then to take some action when that count reaches certain value. So we'll see that the functions of these timers in little bit detail, and how the registers are being used, what are the bits that are being utilized in this case. So we'll have a quick look at that. So to understand the timers and counters, these are some of the registers basically. We were discussing last time about the memory registers. So each timer and counter will be reserving 3 words. So whenever I'm creating one timer, it will be reserving 3 words or 316-bit location inside the PLC. So that is how whenever you create the timers, it will be occupying the memory accordingly. So what are these 3 registers that we need to see? So like this, so this is the data file. If you can look into timer data file is there. So T4, T is the file type and 4 is the file number. So by default, we will be taking T4. So file number 4 here. And then inside this file, you will see that each timer will be occupying 3 words. So word 0, word 1, and word 2. And each of them are 16-bit values, 60 to 15. Now in these 3 words, if you see that word 0, we have only used, or the manufacturer of the PLC has only utilized 3 bits only. Out of the 16 bits, only 3 bits are defined right now, and rest of the bits are being left undefined, and they may be kept for the future expansion. So whenever we will be addressing the particular bit, because this compiler for this PLCs normally allow us to address them with a name actually. So these bits are named as DN bit, timer ticking bit, and the enable bit. There are 3 bits basically. You can directly address by the names, or in spite of the name, you can also address them with the bit number. Last time we have seen that we have put a slash on the word, and then we have added the bit number. So now in this case, we will see that the 3 words that are being used over here. Word 1 is used to store the preset value here, and preset value is the value for which the timer is ticking, the maximum value that it can take, and that you can find it out because it's a 16-bit long register. So 2 raised power 16 is the maximum preset value that you can add. This is something around 65,535. So I think 535. So around 65,000 timer ticks you can have. Then the word 2 is storing an accumulated value. As the timer is running, at any point of time, you can check how many ticks has been passed actually, and how much time has been lapsed. That can be calculated from it. So this is how the 3 words are being used. Same is with the 3 words being used in the counter data file also. In counter, we have a few additional bits that are being used. We'll discuss when we discuss the counter. So these are the done bit, count up, count down, done, overflow, underflow. These are the 5 bits that are being used in the counters. Let's understand the functionality of the timer. That is very important. Now, when we talk about the on delay timer, let's try to understand how it will be behaving actually when I will be using this in the logic circuit. So in on delay timer, if you see here, there's an input that I have to connect over here, and that is what we are using as an in here. So with this timing diagram, we will try to understand how the timer is behaving. So this is an input here, and then you will be having an accumulated value inside this. Then we have 3 bits, enable bit, timer ticking bit, and done bit. So only 2 are available for connection outside, but timer ticking bit is operating internally, and it will be changing in the corresponding word actually inside the the timer registers. So now let's see that how the behavior of the timer will work. So if you have to use in the ladder logic, what I have to do, I have to just draw this timer block inside this, and I will be connecting some kind of an input to this, and that is how the timer will be configured to operate in the ladder logic. Now let's start from this when the everything is at 0. So this is indicating a level 0 or 1. So this is 0. This is 0 and this is 1. So for all the timing pulses over here, you can assume this is 0 and this is 1. Now what will happen before we start observing this timer, everything is at 0. So your input is 0 means this is false. There is no input available over here. Then your accumulated value is 0. Your enable bit is also 0. Your timer ticking bit is also 0 and your done bit is also 0. It means all the bits are 0. Now, what will happen when the input is available? So for example, now this point of time, if you can see here, this input is now changed from 0 to 1. It means that whatever input you have connected over here, whether it's in a switch or a proximity sensor, proximity switch, it will be giving this high value. This is true. The moment it is true, I'm representing this with this pulse area. So if you see that the input state changes from 0 to 1. Now what will happen when the on delay timer, the input is true? Fine. And if you understand the terminology, it says on delay. I would like to create a delay in making something on. It means that if I press the push button, if I give some input to the system, my output will not on immediately. I would like to create a delay that, for example, I will say that the device which is connected to output will get on after 15 seconds. Or I can say that once I press a button, the fan will start after 5 minutes. Something should be there. So your actual output will not go on immediately. In the previous logic, whenever you have connected this input and to the output instruction, at the moment this is true, this is true. The moment this is false, this will be false. Fine. But if I want to create any kind of a timing delays here, I would like to control the output in a way that output will get on after some time. Fine. So that is known as timer on delay. That I would like to delay the on time of the output. If you want to understand this way, that I would like to delay the on time of the output. It means that whenever the input is true, the output will not be true immediately. So I will be controlling the output in the timers with the help of a done bit actually. So this done bit is used to, so there is no output directly coming out from the T on which will be connected to the device. Only a particular bit is setting inside the timer registers. And I will be utilizing this done bit to control my output here. Fine. So in that case, let me quickly show you. Otherwise you might have done it also, but let me just draw it for quick understanding. So what we will do, we will be using any input over here, and then I will be connecting this to the, I'm not drawing the whole block as such. I'm just mentioning this is in a T on block. And then the rest of the enable and then done. These are the two bits that are there. Now, what I will be doing, this is the input here. So for example, this is an input coming from the S1 push button. Then I would like to control an output over here. This is an output which will be controlled, but this output will be controlled by one of the bit of the timer. So in this case, this will be the done bit actually. And this I can consider this could be in a solenoid of an actuator like this. So this is the way you will be utilizing the done bit of the timer to control an output here. So this is how the output is being controlled. It means that I will be looking forward for the state of the done bit when this input is available. So if you can see here, once this input is true, my done bit is not true, it's still false. It means that the output which is connected to the done bit is still false. This is true, but this is false. But this true will make my timer starts. It's like in a stopwatch. You have just press the stopwatch button and your time start ticking. So that is how you will find that your timer is enabled. The moment this input is available, your timer is enabled so that this input pulse is, the enable pulse is high. So enabled input is now high here. And your timer start ticking, means timer now start incrementing this value. So ticking value will be incrementing. That is how your TT bit is also true. What you have seen that your timer is enabled, your timer start ticking the moment your input is high. And your accumulated values will start incrementing. So this accumulated value is 0 initially, but the moment this input is available now, based on the time base, it will start ticking. It means that the timer count will be, or the accumulated value count will be incrementing. So it will be going from 0, 1, 2, 3, 4, 5, and so on. It will keep on ticking. It will go up to the preset value. So this is the preset value. The timer will keep ticking till the preset value reach. But please note that during that time, your input should remain high. So once I make the input high here, my input should remain high till the timer is ticking, till the timer is running and it will be reaching to the preset value. So what will be happening? Your accumulated value will be increasing. Your enable is completely dependent on the input because that is how it is connected. So this is the input and this is the enable, which is directly connected to the other side. So the moment this input is available, your enable is true. So that is how enable behavior is almost like an input. So whatever is available as an input, that enable bit is also true because this is the way it is completing this instruction here. So most important part we need to observe now the timer ticking actually. Till what time the timer will tick? The timer will keep ticking till the accumulated value reaches the preset value. So this is the time it will be incrementing. And once it reaches the preset value, the accumulated value will be now, because timer stopped ticking now. At this point, there is no further increment. So timer stopped ticking now. The moment this preset value matches with the accumulated value, this timer stopped ticking, and that's how the TT bit will false. It will go 0, 1 to 0. At this point of time, your input is still high, your timer is still enabled, but the accumulated value matches the preset value here. And that is why the timer stopped ticking, because the time delay has reached now. And now you want to take some action because I have created a delay. Whatever delay is required, now I have accounted for that delay. Let's say that if it was in this case, it is in a 400 seconds. So 400 seconds lapsed now. At this point of time, I would like to make the output on. So DN bit will be true now. So DN bit will be true. So this moment you will find that the DN bit is high. Fine. So done bit is true. Done bit is true at this point of time. When the accumulated value matches the preset value, your timer stops ticking at this moment and your input will be high at this point of time. It means that I have created a delay. The moment this input was true, I made the output true after some time. And this is the delay that has been created. This is the delay that has been created. This is the delta T that has been created here. So that is the way you have created a delay between the time that has been lapsed in between the input is true and the time that lapsed when the done bit is set. So after this input, the done bit is set after some time. Right? This is the normal behavior where the input will remain high. Please note that for keep timer ticking, your input should remain high. Now please remember, now if I connect this S1 as a push button here. So what will happen if I press the push button? Your timer is on, but then in that case I have to keep this S1 on. This S1 should be on, otherwise the moment you release S1, timer will change differently. Timer behavior will change. So let's see the scenario when you have released the S1 before the time lapsed. So this graph also shows the another condition. So first condition is up to here, which is now clearly explained that the moment the preset value matches the accumulated value, your done bit is true. And this done bit will remain true till your input will remain true. So that is how you will find this. The moment the input falls to 0, everything is going to reset again, because now I will be making timer available for the next operation. It means that the accumulated value will go to zero value again. Enable bit is zero, TT is already zero, and done bit is also reached to zero. So everything will be initialized to this position again, which was there here before the timer was starting. So now timer is ready to start next time. And second time, if you see here, I have started this timer by this input, which is available at this point when this is true at this moment. So your accumulated value start incrementing, your enable is true, your timer start ticking. But if you see here, before the accumulated value reaches the preset value, this input goes false. So this input which is available to this timer may not be kept on till the delay that you want to create. So in that case, what will happen? The moment input goes zero, everything will reset again. So accumulated value will go zero. This will go zero. This will go zero. And this done bit will not set. Done bit will only set when the accumulated value matches the preset value. And this has not happened in this case. So we have truncated this accumulated value, which is rising up to the preset value. It has been reset to zero before the time that we are expecting will be delayed here. So 400 before 400 second, if you release this input, if you release this push button, your timer will reset again. So that is the reason that at this point of time, done bit has not been set here, because the delay has not happened. It's almost like that you press a push button. Then, for example, if you want to make the fan on after 10 minutes, so you have to keep this input on for 10 minutes. Fine. Then only let's take an example. For example, we want to start a fan inside a room only when person will be there for some time. Let's take this example. So sometimes people keep coming inside the room and then going outside. So let's not start the fan at that point of time. So what we want, the person should be inside the room and he will be there for some time, then only the fan will start. So that is the way you can use an proximity a PIR sensor, that's a passive infrared sensor, to detect the presence of a person. And based on that input, you will be running the fan. So it will not be starting immediately. Otherwise, what will happen? If the person go in and out 3 times in a minute or so, then the fan will make on and off, on and off, on and off. This cycle will continue. So avoiding that, we would like the person to be sitting and stable inside the room, then start the fan. So that scenario is just an example to understand that the moment person left before 10 minutes, whatever you have designed, fan will not start. Again, next time, whenever he will enter the room again, so at this point, he will be entering again. So this sensor will be giving you high, and he will be there for the complete delay time, that whatever we want, whether it's in a 10 minute or something like that. So he will be there for 10 minutes. His accumulated value reaches the preset value, then your done bit will be set. And this done bit will be on till this input will remain on. So till the person will be in the will be in the room, the fan will keep running. And the moment he left the room, immediately the fan will go off. So did you understand this example of the on delay timer? So two scenarios we discussed. One is that you will be keeping the input on till the timer ticks for the complete preset value, whatever you want. And second case we have taken when the timer, the input is being taken off before the timer reaches the preset value. So the two scenarios. The first case, your output will be on based on the done bit. So done bit status will be 1 in this case. And the second case, because time has not lapsed here, so you have not kept a delay. You have not been patient enough to keep the input high for the delay time. That's a reason that the output will not be on. So you reset the timer before it spend the time that you want to create a delay. Hope everyone understood this. You can raise your hands also if you see that, yeah, if you are not speaking, at least you can raise your hands to indicate that you have understood this. Good. So on delay timer functionality is clear. And once you have, yeah, I see few hands are there. Yeah, good. So if there is no problem in understanding this, we can go ahead. Yeah, good. Thanks for raising your hands. You can make them down. Good. So I assume that all of you have understood this concept of the on delay timer. And as I have already explained an example, similarly, we'll see more examples when the on delay timer can be used. Now there's another timer which is known as off delay timer. Now the behavior of the off delay timer is different than the on delay timer, and the term itself says the off delay. So we want to delay making something off. Fine. So let's see that last time what we have done, that the moment the person left the room, we immediately switch off the fan. Yeah. And many times if you have seen in the hotel rooms that there's a key which will be making the power on inside the room. But when you take out the key from that key holder, the power will not go off immediately. Have you observed that? So that whenever you take out the key, because the moment you take out the key, the room will be in the dark. So it will be difficult to look at anything. And then even how to bolt the room, and then you may not be able to pick up your items also. So that is the reason that we want that once the person take out the key from the key holder, I would like to make the lights off in the room after some time. So that is what is known as off delay. The moment you put the key in the key holder, the lights will be on. The moment you take out the key from the key holder, light will be off after some time. So it means that I have created a delay in making something off, not making on. The last time what we have done, we have created a delay in making something on. That I have created a delay in making the fan on. This time I will be making the delay in making the light off. So that is what the off delay timer is. So the functionality, if you can see here, the moment input is true. Now you have understood the previous graph. Then if you see that the moment input is true, your done bit is set. It means that the output is immediately on. But your timer will not be starting because I am not interested when you made the device on. I am interested whenever you remove the key. I'm interested whenever you make the input on in this case, right? So if you see here, sorry, off in this case. So the moment you place the key in the key holder, input is true. You have some sensor inside that. And the moment I take out the key at this point, so at this point, what I have done, I have taken out the key. I would like to count the time from now. So then there is a delay that I would like to create. So this is the delay that has been created. So I can safely say 15-second delay. Or in this case, it's in a 500 seconds delay. Anything can be defined here. So that after the 500 seconds, my output will go off. Now, if you see the behavior of the timer here, this input is true. Your done bit is true. It means output is on. Timer is enabled, but it is not running. So enabling the timer and running a timer is the other two different things actually. And running the timer we call the timer ticking actually. So in that case, this TT bit is not high. It means the timer is not ticking. When the timer is not ticking during the duration, it means that the accumulated value is not rising. It will be at zero only. Fine. Now, after this point of time, this input will be on, and then I just take out the key at this moment that I have made this input 0. Now I would like to start timer from here. I would like to start the stopwatch from here. I would like to start counting the time from here. So from here, I will be now starting the timer. That is how the TT bit will be set now. The timer start running. TT bit indicate that timer is ticking, that timer is starting. And then your accumulated value during that time will be increasing. So accumulated value will be increasing and rest of the behavior will remain same, that once the accumulated value reaches the preset value, I would like to make the device off. So then you see that the DN bit will remain on, and only at this point of time when the accumulated value matches the preset value, this will go off. So your output will be off at this point of time, and then your timer stop ticking at this point of time. And then this is how the off delay has been created. Now, in this case, what will happen if you take out the key and before the 15 seconds or whatever time that you have kept for keeping the light off, you realize that you have left something in the room. You place the key again in the key holder. So then the lights will never go off. So that is the behavior that you can see here, that this done bit will remain true. If you place the key again, it means that I will be making the input again before the time lapsed. So I'm just giving you the analogy and the behavior of the way that you are using the key in the hotel room so that you'll understand the application more clearly. So in this case, what happened in this second case, that you take out the key and you want to go out of the room, and then by whatever is the delay that has been programmed, before that time you realize that you want to again go inside the room and then want to search something, then you place the key back. So you take out the key and then you place the key back before the delay has been lapsed in this case. So that in that case, the room slide will not go off. It will remain on because we have not waited for that delay time. And that is how that it has been reset at this point of time. And again, this will be ready to take up the timer input again next time. So what will happen again, you will see that I have again have the input available, and then this input will be basically again resetting the timer, and it will start ticking next time again, and it keep waiting for this. So the moment your input is off, timer start ticking, accumulated value start rising to the preset value. The moment the accumulated value matches with the preset value, your done bit will be set, and then the action of the done bit will be to go 0 in case of an off delay timer, and in case of an on delay timer, it will go on, because I would like to make device on, and here we would like to make the device off. So these are the two type of timers commonly used in many applications. So that is how, once you understand the behavior of the timer, then you can easily use it inside the ladder logic. So I hope this off delay timer will also be clear. So on delay timer, create a delay in the beginning itself. Off delay timer, creating a delay in making something off. That is how the off delay timer is being used. Then there's a reset bit which is used to reset the timers and counters at any time. So anytime, if you see here, this timer is running, but it is getting reset on its own after the input goes off. That is one way that by default it is dependent on the input. But in between also, when this is input is high, for example, in this case, input is high, timer is still there, and I would like to reset the timer. Since then this there's an instruction to reset the timer. There is an instruction which is known as RES instruction. So RES you have to see here and then put into the braces like this. So this is, and then you place the address here. T4:2 is the timer that is of the second timer here. So 0, 1, 2, it's the third timer. So T4 is the file, and then there you will be creating multiple timers 0, 1, 2, 3, 4, and depending on the memory available inside the timer file, you can create so many timers, and each timer will be reserving 3 word memory inside the PLC. So that is how it has been used. So with any inputs, I can reset the timer at any point of time. They are not so useful when we talk about the T on and T off. There's another timer which is RTO timer, retentive on delay timer, where uh, the depending on the input, it is not going to reset on its own. So that is what the behavior of the RTO. We are not discussing in today's class. It's not required because we just want to keep the thing simple. But in RTO, that you need to manually reset the timer. It will not be getting reset based on the input that is available. So then you can, otherwise you can use it on the other timers and counters also at any point of time. Whenever you want to intervene in the ongoing timer increment, you can always reset it with the help of this instruction RES. Then there's an accumulated value. We have seen that there's an accumulated value inside the timer here. This accumulated value, you can see that it will be incrementing as the time lapsed. But any point of time, I would like to read it and I would like to take some action, because right now we have not seen the comparative instructions or comparison instructions. But I can compare. See, if I have set a timer of 500, the preset is 500 here. That after 500 seconds, I would like to take some action. So in that case, if I would like to see in between whether the 100 seconds lapsed or 200 seconds lapsed or 300 seconds lapsed, so that part you can read from the accumulated value. Now, how can I access the accumulated value register? That is what is being discussed over here. That you can access this accumulated value register by the name of the register itself, name of the word. So one option could be that you could be addressing the word 0, 1, 2. That is possibility. So T4 colon 2 dot is the, now we are referring in the slot. Basically earlier you have seen this is the slot number, but in this case it's in a timer number actually. So T4 is a timer file colon, then this is the timer number. And within that timer dot, we will be placing the word actually. And so we have three words as I was mentioning: accumulated, preset, and then there is a status word which is indicating the done bit or the enable bit or the TT bit that can be accessible here. So when I was explaining this, yeah. So we have this word here, word 1 here, and the word 2 here, like this. So I can read out the, so this could be the pre, this could be the accumulated one. So I can directly address them with this also. Otherwise, I can put the number 1 and 2 also. So same way in this case, if I would like to read the accumulated value at any point of time, I could use this addressing scheme T4 file number, file type, file number, and then the timer number over here, and the dot is indicating the word here. Fine. And if within that, if you place slash, and then this will be talking about the bit actually. But accumulated and preset, we don't need the bit level information. I'm interested in how much is the value inside this. So then based on the comparison instruction, I can write a different program to compare and check and take some action on that. And so that for that, we will be reading this accumulated value and the pre-value registers. Then to read the done bits, we will be just placing slash dn, because slash is indicating the, so we'll not be writing the register 0. It's understood that if you are just placing T4 colon 2 slash dn, this is mean that this is referring to the done bit of this timer. Same way you can refer to the enable bit, you can refer to the TT bit. Any point of time you can read this bit state and you can take some action accordingly. So done bit, as I was mentioning, that you have to utilize the done bit to make the output on, and rest of the bits may not require it just for the debugging, or you just want to check some state of the timer. For that you can use the enable and TT bit, but to control the output we will be using the done bit in this case. So that is how you will be using another input in the ladder logic, and the state of this bit you can define, the address of this bit you can define like this done bit. So once the timer is making this done bit high, the output connected to this will also be high. And then I will be able to control the output devices with the timers and counters. So that is how the accumulated value can be used. Now quickly talk about the counters. Once you understood the timers, counters, as I was mentioning, they are almost same as the timers. Only thing is that they are not incrementing on their own. As in the timer, once you start the timer, the internal count value will keep on incrementing every second, every millisecond, whatever time base you can use. In case of a count up and count down, they will only be changing with the state of the input. So one count will be like this. So whenever the rising edge of the incoming pulse here will be there, it will be incrementing the count. Accumulated value will change. So every time you press the push button like this, if you are using a push button, and then every time you press the push button, one pulse will be generated like this, and then it will come back. So every time, so there is nothing happening in the pulse falling edge. It means that whenever it is coming from 1 to 0, there is no change in the counter value. Only when the rising value will be there, only when the rising edge will be there, the count value is incremented by 1. So the 1, 2, and so on. So at all the rising edges, the count value will be incrementing, right? And that is how the count up will be keep on incrementing the accumulated value count. That you are starting with a 0 in this case, you have a preset 100. So every input pulse on this will increment this count as 1. Next pulse will increment 2 and so on. And what will happen again in the case this accumulated value matches with the preset value whenever it is greater than or equal to preset value, the done bit will be set. Fine. So then you can take some action when the objects being counted. For example, if you are filling something into a carton or there's in a box, you are packing something. So you will be counting how many objects are passing on the conveyors. For example, if you have a conveyor, you have a proximity switch here. And then I will be counting the box moving or the items moving on the conveyor and falling into the box. So once that 100 items being dropped into the box, I would like to stop the conveyor and then move the packing box to the different conveyor. So there what you will be doing, you will be keeping track of the objects being dropped inside the box with the help of a counter. In the moment 100 objects being dropped, this done bit will be set. And then with the done bit, I can start the next conveyor so that the box will move forward and the empty box will come again below the location where the parts are being dropped. So that is the way counters can be used. But the change that you can see here earlier, the input is making a lot of impact on the timer functionality. Input is not impacting the counter functionality to that extent. It is only just incrementing the count inside. So in that case, how to reset? Basically, once the 100 objects being counted, if there is another object coming up or if there is another pulse available now, after the 100 accumulated value reaches the 100 value. So what will happen? It will go to 101. It's not resetting on its own. So next time, if I would like to count 100 objects again, I have to reset the counter. I have to bring it to 0, count accumulated value 0. Then only the next time I will count 1, 2, 3 and so on. And only then the preset value matches with the accumulated value. Again, the done bit will be set. If you will not reset the count up or the up counter, then what will happen? The count value will keep on increasing 101, 102, 103 and so on. And the done bit state will always be on. It will not be reflecting again the change of the done bit will happen. So that is the way after you take some action after the accumulated value matches with the preset value. And if the accumulated value is greater than preset value, still the done bit will remain on. So you have to reset the counter by some means actually. So then you need some input which will reset the counter. So then we will be using that reset instruction, what I was showing you earlier. So you can just use that instruction C5:0. So then you will be resetting the counter and then again it will start from the accumulated value 0. So this is the way you can reuse this counter. So count up is there to increase the count value. Whenever you use the programming software, you can see on the left hand side, you will see any of the registers of the PLC. So whatever files we were discussing, you can just double click on the data file or on the counter. You will see this kind of a register, which will show you all the bits and all the register value, all the word that I was just mentioning. You can also visualize them. That is how you can take it. Fine. Overflow and underflow is something which is basically counting beyond. So as I was saying, if you are not resetting the counter, and if you just count it up to the maximum value, that is 65,535, if you still give the second value, then the counter will overflow. It will come down to 0, count will come down to 0, but then it will generate a flag that is counter is overflow. Fine. So that may be sometimes used to take some action in that case. Fine. Same is that underflow will happen once you are using a countdown. So overflow is happening when you are counting up, and underflow will happen once you are counting down. So similar timer is the CTD, which is a countdown, and countdown is basically decreasing the value. So in this case, this is not written correctly. What we want to have, accumulated value decrement every time the input is available. So if you are having a 0 over here, then it will go to -1 actually. That doesn't help. So what we want to have here in this case, accumulated value should be higher. So this is not correct. So I will be just keeping this in the accumulated value, and let's make the preset value 0. Now in this case, every time the input pulse is available, every time this input pulse is available, my time this counter value will go down. So it means that it will go 199 and it will go 198 and so on. And the moment it reaches to the 0, then the done bit will be set in this case. So one timer is to increment the count, another timer is to decrement the count. Why we need to? Because the advantage is that we can combine these together into one single counter. So you can use the same address on the CTD and you can use the same address on the CTU. So I can have two inputs, but I can keep record of the total value inside the single counter. Let me give you an example of a parking. So you have a parking space and you can put a barrier at the entry and you have a barrier at the exit. So you have one sensor at the incoming barrier, one sensor at the outgoing barrier. So at any point of time, if you want to keep record how many vehicle or how many cars are there in the parking lot, you will get that value from the accumulated value of this. How it will work? The moment the car goes inside the parking, your incoming sensor will increment the count. So it will increment the count accumulated value to 1. Start from 0. So one car goes inside the parking. The moment this car left out from the second gate, that is the outgoing gate, then we would like to decrement this count again. So earlier you have used the CTU. Now I would like to decrement this count. I will use CTD. So one input will be incrementing the count value, other input will be decrementing the count value. So ultimately at any point of time, we'll know that how many cars are in the parking lot. So that is the way timers CTU and CTD can be combined into one single address and they will be maintaining in a common accumulator. So that is the advantage of having both the timer CTU and CTD, and you can use them individually if you want to use them, but individually CTU and CTD almost same because they are just counting the objects whether it will be incrementing or decrementing, and on preset value you will be taking some action. But if you combine them together, then it makes more sense in the kind of application that I have explained, that is the parking application, where you can have at any point of time you have a record of that how many cars are there, how many vehicles are there. So that is how the CTD can be used. Fine. So these are the problems that we can do. Many times we conduct this quiz, but let's see that if you can attempt on your own. So what I will be doing, I will be leaving these problems to you. And tomorrow we will discuss the solution of that. So hopefully then you will try to attempt these problems on your own. So this timer problem is that you have hot pressing die here. So there's a hot pressing die. You are packing something. So it will be heating some surface and then keeping that heating on for some time. And then it will go back. So this time, whatever is happening, this actuator will be moving forward. It will remain there on this cylinder for some time. So the packing will happen and then it will go back. So coming down, hold here for some 5 seconds over here. And after 5 seconds, it will go back. So now you have to implement the timer. So by pressing a start push button here, the heating rail is advanced and the packing material is heated along the adhesive strip. The operation will take 5 seconds and then heating rail will return to its start position. So this is the problem statement. Now what you have to do, you have to use some sensors also here. So they are not marked here. So 1B1 and 1B2 are the two sensors that I can add on over here. You can have an S1 as a push button here because there's a start push button. And then you have the two solenoids over here, 1Y1 and 1Y2. Now what you have to do, you have to draw the connection diagram. So first thing that you have to do, you have to draw the PLC connection diagram for this problem. And then you have to draw the ladder logic here. Please do this. I think that's one problem. The second problem is this counter example. Whatever we have learned right now, we have to attempt this also. It's a counter example. Now what we have to do, so there's a feeder basically. So there's a magazine which is in a gravity fed that items are coming out and then they will be replaced by the previous item by the gravity only. So they are stacked one after another, and you will be ejecting the part from this gravity fed magazine by a cylinder. So every time you press a push button, and a part will be coming out of this magazine. So if push button S1 is actuated, cylinder is to advance, eject a workpiece, and then retract again. So that is one cycle. You press S1, cylinder will go forward, it will come back, and it ejects one part from the magazine. But then I would like to keep a track of this, how many parts are being ejected. So that is how we will be doing here. So we will be counting 15 parts in this way. So 15 parts are to be ejected in this way. And when 15 parts have been ejected, it should no longer be possible to trigger a cylinder movement. So I would like to stop it now. So if I press the S1 16 time, the part will not come out. So that is what is to be implemented. So it should no longer be possible to trigger a cylinder movement by push button S1. Only when you press another push button S2, I will be again ejecting 15 parts further. So you have this kind of power with the supervisor that unless he press S2, he cannot continue the operation for the next cycle. So operator can eject 15 parts, then supervisor has to give one input that through the S2. Then again, the operator will continue with another 15 parts and so on the cycle goes. So every time after 15 parts, it requires some intervention to control the operation, how many parts being, how many cartons being prepared or how many objects are being packed like this. So this is the same problem with the counter. It can be attempted. So you have to identify whether you have to use CTU, CTD, on delay timer, off delay timer in the previous example. So that these are the two problems. So please try to attempt these two problems before we discuss the solution in the next class.